So let's take a look at stochastic matrices. Let's begin by thinking about the states of a system. Let's say we have an automatic door. An automatic door is open or it's closed, and we can think of, in the simplest sense, that the possibilities are that it's open and it transitions to closed, or the door is closed and it transitions to open. This doesn't quite achieve the overall goal, though, of describing all the possibilities for an automatic door. Because a door that's open can stay open, and a door that's closed can stay closed, so this is a little closer to the states of the system. So if the door is open, it can either stay open or transition to closed. If it's closed, it can stay closed or transition to open if someone approaches. But even that doesn't quite get the full picture. We still have the possibility of the door being open, the door being closed, and staying in those positions. But there's a little bit more to it, because a door that is closed can start to open. It's not opened all the way, but it's in an opening state. Before it's open, it's neither closed nor open. It's an opening state in that case. And so we can transition from closed to opening and then on to open. Then there's the other direction. We have the closing door, so we can transition from open to closing and then on to closed. But we usually have a safety feature in a door. If a door is in the process of closing and someone comes in, then it transitions to opening. And so if the door is closing, it can proceed on to closed, or it could transition to opening and go back to being an open door if someone approaches or if something gets in the way of the door closing. And we could add possibly other loops and so on, but we're talking about a change from a door that's closing and still closing. Maybe if we have time steps associated with this, then we might stay in that state and have loops there and so on. But the general idea of describing different states of a system and transitioning from one state to another state depending on other scenarios, other information that's coming in. So we're going to take this idea, and instead of drawing pictures, we're going to do calculations. So we will first of all think about probability vectors. So we're going to think about a discrete probability vector. A discrete probability vector has non-negative real entries, and the sum of all of the entries is 1. In the way we're going to use these probability vectors, the dimension of the vector will correspond to the number of states in the corresponding system. So whatever number of states there will be one value in the vector for each one of those states. And so the probability aspect then is the entry in the vector represents the probability that the system is in that state at that particular time. If we know the state, then the corresponding entry is a 1 and all the other entries are 0. But if we don't know the state, then the entries will be probabilities that are greater than 0, less than 1 in most cases. If we know exact information about a particular state, maybe we don't know for sure which state we are in, but we know we're not in that state, then that state has a value of 0, and the other states have values that are something less than 1, but still positive because they're probabilities. So that's a particular situation of describing which state do we think we're in right now. A stochastic matrix is going to be the bigger sense of describing the system. So stochastic corresponds to things that are changing based on probabilities. So a stochastic matrix consists of probability vectors. Which state are you in, or which state will you be in the next time step? But again, the probability vectors that make up the matrix all sum to 1. They're all non-negative real numbers. And so the idea is we're going to describe the possible changes in the system and give the probabilities of transitioning from one state to other states. Other names for stochastic matrices are probability matrix, transition matrix, or Markov matrix, named after the Russian mathematician Andrei Markov. And so these show up in a lot of different settings, a lot of different applications, just times when things are changing based on a probabilistic approach, a probabilistic aspect of whatever the system happens to be. So with stochastic matrices, there are right and left stochastic matrices. A right stochastic matrix, we're going to write as P sub R, the P corresponding to it's a probability matrix, and the R just meaning that it's a right stochastic matrix. And in this situation, the rows are the probability vectors. So the rows sum to 1. And the entry ij, so row I, column j, is describing the probability of transitioning from the meaning of that row to the meaning of that column. So if we number all of the states, then entry ij says we're transitioning from state I to state j. For a left stochastic matrix, the idea is that it's the columns rather than the rows that are the probability vectors. So this is a transpose of the right matrix. The sum of each column is 1 in this case, and entry ij, so row I, column j, is transitioning from j to I. So in the right stochastic matrix, you can think of the rows as the transition from the row to the column, and in the left stochastic matrix, it's the other way around. So in a weather situation, let's suppose that we have 3 possible weather conditions. We have sunny, cloudy, and rainy. So no other conditions possible in this setting. So we're going to label each row and each column with an S, C, and an R. And we just make up some numbers here. And let's suppose that our stochastic matrix has these entries to describe the transition from one kind of weather to another kind of weather. So in this particular setting, we are describing what happens in going from the row state to the column state. So the idea here is if it's sunny, there's an 80% chance that the next day will be sunny, a 10% chance of clouds, and a 10% chance of a rainy day. So we sum across that, and if it's sunny today, we have a 100% chance of something happening tomorrow, whether it's sun, clouds, or rain. If we look at other entries, for a rainy day, for example, there's a 40% chance that the next day is cloudy. So go from this row, the rain row, to the cloud column, and we have this value in place. So again, these rows all add up to be 1. So we have the stochastic matrix, and in this particular case, since the rows sum to 1, we have a right stochastic matrix. So we had that right stochastic matrix with the vector x times p, with the matrix being on the right-hand side. If we do the transpose of everything, then we will change the order. And then the calculations, the resulting numbers will be the same. Again, they will just be transposed. Now, when we do this approach, we have what are called stable probability vectors are possible in some settings. Another word or other terms for this are stationary or steady state vectors. And these are probability vectors that are left unchanged after multiplication by the stochastic matrix. Whether it's on the left-hand side or the right-hand side is appropriate. What happens is when we do the calculation with, say, a right stochastic matrix and the vector x, we have this row vector x times the right stochastic matrix, and we get back the same vector. Right? It's unchanged by the calculation. For a left stochastic matrix, it's the same thing, only the matrix multiplication being on the left, and reusing the name for the vector, but remembering that in one case it was a row, and in the other case it's a column. Okay, so what happens here is that we get this idea of the vector times the matrix in the appropriate order is equal to the vector. And so a probability vector is stable or a steady state vector for a system described by the matrix P if that vector is a probability vector, first of all, and it's an eigenvector of P that corresponds to the eigenvalue of 1. So let's take a look at the problem of a mouse in a maze. This mouse is going to be placed into one of the rooms in the maze, not into a trap. And there are doorways all around through this maze. And so if the mouse, suppose it starts here in the upper left-hand corner, it has 4 options of doors it could take. It selects one of those. Let's suppose it selects the door to the right. Now it's in this room. Again, it has 4 options. It can run back and forth between the same 2 rooms a bunch of times if it likes. That's a possibility. One time step to the next time step. It can move up or down, left or right at each point. If the mouse ever leaves the maze, it escapes to the outside, that is a state as well, but it's free and it stays out there. So this is a state that has a loop back to itself but doesn't go anywhere else. So once we reach the outside, we're out there forever and we're free. Otherwise, we're moving around inside the maze, and what may happen is the mouse may enter into the trap. Now in this setting, once it enters into the trap, again, that is a loop back to itself. So once it's in the trap, it stays in the trap forever. It can't go back out of that through any of those doorways. And so there are 2 states, the outside state, the free state, and the inside state, the trap state, that have loops back to themselves and don't go anywhere else. All the others have possibilities of going different places. So in this setting, we could number the rooms from 1 to 9. Let's say we start at the upper left-hand corner and just number across. And then the top right room then is 4. The trap in that particular situation would have been in room 7. And freedom is room 9. You don't have to number them this way. You could number them however you like, but we just have to number them so that we know which row and which column corresponds to various aspects of the system. So which row represents this state, which column represents this other state, and so on. We just have to make it clear somewhere. So this is a way to do it. Any choices you make. Of course, if you're using the matrix class or using NumPy, then this indexing begins at 0, so we do that offset rather than numbering from 1 to 9. We do that offset for the calculations, but the idea is still the same, that a particular row represents a particular state, a particular column represents, again, its particular state as well. So in the right stochastic matrix, this is where the rows will sum to 1. The first row will be we're not worrying about the mouse staying in the same room. While it's in the same room, we're not considering a transition to have occurred yet. So what happens? There are 4 doors out of that room. One of them goes into room number 2. One of them goes into room number 5, which is the one below it. And 2 of them go to room 9, which is the freedom to the outside. And so we have a fourth, and a half for the first row of the right stochastic matrix describing this maze that has 8 rooms, 1 trap, and freedom on the outside. The 9th row of this would correspond to if you are already in the freedom state, right? You're outside the maze. What happens? You stay outside the maze. So you don't go back into the maze at any point. These are all zeros. You are outside. You stay outside. And then there are all the other rows. One of those will also have all zeros except a single one. And all of the others will have a mixture of halves and fourths that show up. So in getting this mouse out of the maze, we're going to begin with the mouse in a particular room. We just decide which room we're going to start in. We can drop it in from the top. So that start vector has a 1 in that particular spot and zeros everywhere else. And we would multiply x by p to determine the probability of where the mouse is after one step. We don't know where that's going to be. It's going to be probabilistic because we don't know which choices the mouse is going to make, but we know the probabilities of where the mouse is after a single step. And so we would just repeat this process until there are only 2 non-zero entries left in the output. Where will the non-zero entries be? There will be a non-zero entry in the position representing the trap and a non-zero entry in the position representing freedom. Because what will happen in this case? Eventually the mouse will either be trapped or will escape. Those are the only 2 long-term options in this particular system. The mouse might run back and forth, back and forth, back and forth a lot of times, but if it's really doing this randomly at each step, then eventually one of those 2 outcomes will occur. And so to calculate that, one way to calculate this would be we start with x, we calculate x times p, and then take that answer and multiply by p, and take that answer and multiply by p, and so on. So that's x times p squared, x times p cubed, and so on, eventually until the output is a vector with just 2 non-zero entries. So again, what do those entries mean? The zeros means that you're not going to end in that particular room. And the ones that aren't zero mean that this is the probability of ending in this spot versus the probability of ending in the other spot. The 2 spots are, again, the trap or freedom. We add those 2 numbers together. They will be 1 because one of those 2 things will happen. Now, a larger version of this problem has a 5x5 maze with a trap right in the dead center. Even larger versions, we can go as big as you like and put the trap wherever you like according to choices. But If we have a 5 by 5 maze with a trap in the center, that means we have 25 rooms plus the outside. So 26 positions, 26 states in our system. And so we have this 26 by 26 matrix. But we don't need to do the calculations necessarily with a 26 by 26 matrix. We can reduce that by looking at some symmetry. So for instance, all four corners behave exactly the same. There are two doors to the outside, two doors to other rooms on the inside, and the distance away from the trap is the same for all of those because we put the trap in the dead center of the maze. If we put the trap somewhere else, then the corners wouldn't necessarily behave the same. Even though they have two doors to the outside and two doors to other rooms, the distance to the trap wouldn't be the same, and so the corners wouldn't behave the same. But in this particular setting, we have the trap right in the center, and so the corners are all exactly the same. If we look at the top row of rooms from left to right and look at how close you are to escaping versus how close you are to going into the trap, this top row of rooms from left to right behaves exactly like the last column of rooms from top to bottom. The same distance to the outside, the same distance to the trap in the corresponding position. So you have like room 1, 2, 3, 4, and so on across the top. But what's happening is we can renumber the rooms in a way to keep track to say, oh, well, you know, this room is just like that one. So the four corners could all be numbered as room 1 because they are interchangeable. You say, I'm starting in room 1. Well, which room 1? It doesn't matter which room 1. They're all the same. If we continue on around, we see a lot of other similarities around the outside of the grid. And then that kind of symmetry is represented with different rooms toward the trap, going toward the center of the maze as well. But the ones on the outside are different than the ones the next level in because the ones next level in are closer to the trap and further from freedom. And so some of those will be the same as each other, but they won't be the same as the ones on the outside of the maze. And so one way of simplifying this allows us to reduce this to an 8 by 8 matrix instead of a 26 by 26. And if we're doing calculations, remember if the answers are going to be meaningful and be the same numbers, we just have to interpret them in the correct way, and you're dealing with 8 by 8 matrices instead of 26 by 26, then the number of calculations will be greatly reduced. But if we're really thoughtful about this, we might even be able to reduce this matrix even further. Instead of 8 by 8, make it even smaller. And again, the smaller it is, the better it is for our calculations. So what do we have from this whole process? We can describe transitions from state to state in a discrete system by these stochastic matrices. There are also continuous versions of these in a different setting. But we're dealing strictly with discrete system, finite discrete systems even. The initial population distribution, so the probability of being in this state versus that state can be represented as a row or a column vector as appropriate. A stable or steady state vector is unaffected by the stochastic matrix, and often these are the kind of end scenarios of what happens after the system runs for a long period of time. In some cases, you will find out that everything converges to exactly the same thing. It doesn't matter where you start, where the system starts, that you end up with the same probabilities of success or failure at the end. In other settings, it does depend on where you start, and so depends on which vector we start with, what the final answer would be in some cases, and in other cases, it doesn't really matter where we start, the end result is the same. And so the big takeaway from this is just because we can mathematically carry out a calculation doesn't mean that the calculation is meaningful. Okay, we can do the steps, we can calculate something, we can get numbers out of it, it all fits the structure, you can do the calculation, but what does it mean? And that's the important part of all of our matrix calculations. What do they mean? Do they really carry the information that we're wanting to carry? Or do we need to change the order of the calculation or change something else about the corresponding matrix or something about the vector in order to get the answer that we need? So not just do we have the correct numbers, but do we have the correct numbers in the correct place? And so the important aspect, again, to notice is just because you can carry out a step doesn't mean that it's the step you should have carried out. There are units associated, in a sense, with each of these calculations. And so we have to be sure that we're multiplying the correct thing by the other correct thing in order to have a meaningful answer. All right, so as usual, feel free to ask questions in the comments by email or on Discord, and have a great day.